Welcome, everyone. Thank you for joining us for this talk. My name is Gyula Fóra, and this is my colleague Balázs Varga.
Hi, everybody.
We're working in the Flink engineering team at Cloudera to bring Flink support to the enterprise. In our talk today, we're going to talk about Flink SQL, and more specifically, we're going to look at an end-to-end use case involving Kafka, Schema Registry, and Kudu. Before we dive into our use case, let's say a few words about Flink at Cloudera. At Cloudera, we're working on bringing proper enterprise integration and support for deployments both in the public cloud and on-premise in the data center. We have 2 PMC members and a couple other contributors in the Flink engineering team working continuously to improve the integration with other Cloudera services, such as Schema Registry, HBase, and Kudu. Some of these we will see in today's talk. We're also contributing with both code and regular blog posts and talks on conferences. If you're eager to learn more about our platform and product, please listen to our recent keynote from Flink Forward in San Francisco. So now I'm going to give the word to Balázs to talk about the use case that's going to follow us in today's presentation.
Thank you, Gyula. So I will be introducing this use case that's based on a really common use case of enriching some streaming information with some metadata. Specifically, our example today will involve some sensors located on certain machines in factories or plants. And these sensors produce various kinds of readings, such as speed, temperature, or pressure at some machine. And they are used to monitor that these are working properly. So there is this stream of sensor recordings, which will be coming from a Kafka stream in our use case, which will be accessed through Schema Registry for the schema. And the enrichment metadata is coming from Apache Kudu, which Gyula will talk a bit more about later. And these contain information about each sensor on its type and where it's located. We will want to join these two streams, so perform the enrichment, and then group by certain attributes and perform an aggregation to produce alerts. So we want to know if some machines are not working properly, and we produce an average reading of the sensors in case some of them are broken. So we will talk a bit more about this use case throughout this talk, but first Gyula will talk about how we can actually access these data with the help of the Schema Registry and the Kudu catalogs. So now I'm going to hand it back to Gyula.
All right. So the first step in our pipeline is to actually access the data that is coming from Kafka. The Schema Registry provides a centralized metadata storage to track the schemas of the different types of records that flow through our organization. It provides a centralized registry where we can store reusable schema definitions and use this in our data pipelines instead of having to attach it to every piece of record. This is both efficient and also makes it easier to have consistent data definitions across our use cases. Schema Registry also provides version management for the schemas that are stored there. So consumers and producers can select which version of the schema they're depending on, and they can evolve at different rates to adapt to the evolving requirements of the products. We can also use the Schema Registry clients to perform schema validation before write messages to Kafka, which ensures data integrity and a better data quality for our pipelines. Flink, by default, doesn't support an easy way to access the data available in Kafka topics through SQL, people would generally have to write create table statements for the individual Kafka topics. So to avoid this overhead of development and data exploration, we created the Schema Registry SQL Catalog, which lets users access all the Kafka topics that have registered schemas in the Cloudera Schema Registry. For every schema that is defined in the Schema Registry, Flink SQL, the Flink SQL Schema Registry Catalog will create a table for the corresponding Kafka topic automatically, and we can directly access these tables without having to write any create table statements. This allows for a very quick data exploration and prototyping for the users, and also lowers the barrier of entry for people who are coming from the SQL world. Let's look at a quick demo on how the Schema Registry Catalog integration looks in practice. Here we can see the Schema Registry web interface showing us all the schemas that are currently registered in the system. At the moment, we have two schemas registered, one for the recordings and one for the alerts that we're going to create in our example use case. Let's take a closer look at the recording schema. Here we can observe the Avro schema registered for these recordings. We can see the three columns that we're expecting: sensor ID, time, and value. These schemas are versioned, so we can make changes, updating the schemas, evolving them if necessary. We can also simply create a new schema by adding Git on the web interface. First, we have to give a name, a description, we can select the schema type and the schema group. We're going to leave the schema group to Kafka, which signals to Flink that it expects a Kafka topic with the same name as the schema name. Now we can add the schema definition. This is the Avro schema definition. So we create a new record object called name, which contains a first and last name field. Let's save it. Now it's time to switch back to the Flink CLI and take a look at our tables. We can look at the catalogs registered in our CLI. Here we can see that the Schema Registry Catalog is already registered, so let's switch to it. We can see that there is one table for each schema that is registered in Schema Registry, and we can also see the name table that we just created. So let's take a closer look. We can see the columns matching our Avro schema. So let's actually select from this table. At this point, we haven't written anything to this Kafka topic, so our expectation is that we're going to see an empty table result. So it's time to actually insert some values into it. If everything goes correctly, the insert statement is going to insert into this Kafka topic, and it's going to show up on the other side. So now that we've seen how the Schema Registry Kafka integration works for Flink SQL, let's take a look at how the metadata storage side of our enrichment story looks like. For storing the metadata, we use Apache Kudu, which is a columnar storage manager developed specifically for the Hadoop platform. In some sense, Kudu is similar to HBase, but it provides a strongly typed schema that is a better match for SQL queries. Some of the biggest benefits of using Kudu for streaming applications are strong performance for both sequential and random access workloads. We will see this later when we're trying to join our incoming sensor stream with the Kudu enrichment data. Random access performance becomes critical. As I mentioned, Kudu also comes with a nicely structured data model, which is a perfect match for SQL, so we can directly map Kudu tables to Flink SQL tables. And also, Kudu comes with an excellent integration with the Hadoop ecosystem, so various query engines support running queries on top of Kudu, so we can further leverage the data stored there. In order to make Kudu data conveniently accessible from Flink, we have developed a Kudu SQL Catalog. This provides direct access to the tables stored in Kudu. In this catalog, we map every Kudu table to one Flink table and also create table statements, create Kudu tables directly. This is different from, for instance, a generic catalog like the Hive catalog, where we can store any kinds of tables. In the Kudu catalog, we restrict the table types to Kudu tables. Once we have a Kudu table defined in the catalog, Flink reads and manages these tables directly through the Kudu client to provide good performance data access. The Kudu SQL Catalog is part of the Apache Bahir project. It's fully open source. Here you can see the code snippets that are required to define the Kudu catalog. You can see that this is basically as easy as it gets. You only have to define the master address of Kudu, and you can immediately access the tables. Before we go further with our use case, let's take a quick look how the Kudu catalog works in practice and how we can access the tables from Flink SQL. Here on the Kudu web interface, we can see that we have two Kudu tables available, sensors data and sensors. For our demo, we're going to look at the sensors data table, which contains the enrichment information that we're going to use to enrich our sensor readings. We can see the Kudu schema here. We have sensor ID, plant, machine, and sensor type columns, and we're going to later join by sensor ID. The Kudu catalog makes these tables immediately available to use in Flink SQL. Let's take a look at the CLI. We're going to switch to the Kudu catalog. This is the tables. Here we can see the exact same two tables. Let's describe the sensors data table. We can observe the same column definitions, and we can also take a quick look at the data inside. Here we can see a quick sample of the data available in the table. We can see that we have different sensor IDs, and each sensor ID belongs to a plant and a machine in a given plant, together with the sensor type. As you will see later in Balazs's demo, we're going to use this information to enrich our sensor readings and make proper alerts.
So now that we can read data from both Kafka and Kudu using the catalogs, let's get back to our use case. First, I would like to give a quick overview of how joining works in a Flink data stream and unbounded stream context. And for that, let's look at the alternative, or a quick outlook to traditional SQL joins. So in a traditional inner join, or versions of it, such as a natural join, tables are joined on certain attributes, and every row is matched with every row of the other table. So it tries to match this row here with all three of the other table's rows. And it will produce also a finite table based on the combination of these records. So this works because these are finite bounded tables, but some issues arise when one of the tables or both of the tables are in reality unbounded data streams, which is our case with our enrichment use case. So if in Flink SQL we were trying to write something similar to the join we saw on the previous slide with the fields used in our use case, our first try might be something like this, that we want to select every field from these two tables joined using the natural join. You can see that one of the tables comes from the Schema Registry Catalog and the other from the Kudu Catalog. So this approach looks very nice, but unfortunately it is wrong, and our application would crash after a few minutes or hours if we were trying to use this. So let's see what the issue is here. We have this unbounded data stream. This left side represents the sensor recordings coming from Kafka. You can see it has a timestamp, it has a sensor ID, and it has a value. And on the right, we have our Kudu enrichment table of some sensor IDs and the additional metadata. And if we perform this natural join, each row is matched with each row from the other table. So let's see through an example what happens when a new record comes in from Kafka. So this new record comes in, and then it will try to match it with all 5 rows in the sensor IDs table, or the enrichment table. This is not a problem, but the problem comes when we add a new sensor to our system and add that to the sensors table, or the enrichment table. Because when this is added, the same way that it's tried to match the new record with everything on the right, this time it will try to match this new sensor with every record on the left, which is an unbounded stream, which may be days or weeks worth of sensor data. And in order to do that, Flink will keep every previous record from the Kafka stream in its memory, even though this would not be necessary, since before we add this new sensor, we know that it will never produce any records. So even though we know that it wouldn't need to match it with all the previous ones, Flink doesn't really know this. And since our memory is not infinite, we cannot keep everything from an unbounded stream there. So clearly this approach doesn't work like this. So to summarize this issue about joins with Flink, let's look at these few points. So the issue that we outlined is that without unbounded streams, we cannot really keep them in state forever because they are infinite in size. So even when we're performing just some data stream joins, we always specify a window to limit the size of the state that we're dealing with at the time. And similar approach could be used when we're joining this stream with a static, or in our case, it can be a slowly changing append-only table, is that we always want to use the latest version of the table. And we always want to use the version that's available at the time when the record from the unbounded side comes in. So in this case, when a new record comes in from Kafka, we just want to take the current state of the Kudu table and perform the join if possible. And in our use case, we can even know that it will always be possible because the sensor will only emit readings once it's added to this sensors table. And our goal is that Flink doesn't keep the infinite unbounded streams old records. But unfortunately, with a natural join, Flink doesn't know that it needs to do this. So we will outline two solutions. One is to fall back to the DataStream API, and the other one is to use temporal tables and stay in Flink SQL. First solution with the DataStream API involves writing a custom join, which performs this caching or manages the logic of what states to keep. So whenever a sensor data comes in from the Kudu table, so we're starting to read it, and when we encounter sensor data, we cache it in some keyed state. And then when a reading from the Kafka side comes in, we try to look it up in our cache and emit the join result if the enrichment is already available. If it's not yet available because it hasn't yet been read from Kudu, we will just buffer this unmatched stream record and wait until a match arrives from the Kudu side. And then we know we can discard it after it. So the state doesn't grow infinite. It will only keep the records that it doesn't know how to match yet. And the other solution is to use a temporal table, which is a bit of a workaround because temporal tables are usually used for data that has some kind of time component, and the concept of what's a current version or latest version of a table. But this approach will work very nicely for our use case as well. In this way, we stay with the SQL API and treat the sensors data Kudu table as a temporal table. To do that, we need to define a lookup function on the table input, which means that we specify how we can look up a certain data based on some keys. So for this, we actually use the Java client of Kudu. Once we have this lookup function, we can use this syntax that you can see on the slide here, where in the join, we specify that we want to use this sensors data table for the system time as of the processing time of the other recording. So this means that we want to use it as it is at that time point. And this way, it will also know that it needs to discard the old records from Kafka. So this is currently not part of the open source Bahir version of the Kudu connector, but our team is working on adding this functionality as well. So now that we've looked at these two approaches, let's actually see how they work in practice by looking at some example code. Now let's see how this works in practice by taking a look at this simple Flink job that enriches the recording stream coming from Kafka with the sensor data stored in Kudu. This job makes use of both catalogs and uses a temporal table to perform the join. The first few lines are responsible for setting up the environment, registering both of the catalogs, and passing along the configurations. The first SQL statement enhances the recordings table a bit by adding processing time and watermark attributes to it. This is needed because the Schema Registry doesn't know about these attributes, so we have to add it here. We can use Flink 1.11's create table-like syntax, so we can base this table off of this recording table accessed through the catalog, and we name it recording with watermark. We can then use this in the join which is a temporal table join of this new table with the Kudu sensors data table accessed through the Kudu catalog. And we use this for system time as of processing time syntax. But once again, the Kudu table is not really a temporal table in a sense that it doesn't have a time component or a latest version. We just need this temporal table join so that Flink knows not to keep the old records from the Kafka stream forever. And once we have this joined table, we can use it to perform aggregations and create alerts. So here we group in 10-second tumbling windows by the sensor type, plant, and machine. And we compute the average of the recordings in each of these groups. And if it is a really unusual value determined by a user-defined function, then we want to emit an alert. And we can do that once again through the Schema Registry catalog in this alert table or Kafka topic. So I've started running this job along with the data generator, so we can take a look in the Flink CLI using the Schema Registry catalog. We have the recordings table for the generated data, and the pipeline computes the alerts and produces them in the alert topic, which can be accessed through the catalog. So once we get the results, this table should be filled with alerts of the unusual readings. We can see that for each 10-second interval, each machine has the average reading computed, and if it is outside of a predetermined range, then this alert is produced here.
If we need more control over how the join works, or we want to tune the performance a bit, we can use the lower level DataStream API to perform that same join. Let's take a look at this other Flink job that uses this approach. The first few lines of setup are done the same way, and also this time we read both of the recordings and sensor data as tables, but then convert them instantly to data streams. The join itself is performed in this enrichment join class. Let's take a look at it now. So what this does is it keys both streams by the sensor ID and connects them. And then it uses a keyed co-process function to perform the join at a lower level, where we can also manage state. This function is keyed, which means that the state is always scoped to the appropriate sensor ID, and it's a co-process function, so the inputs can come from two sides. If a record comes in from the recording side, then it tries to enrich it with data that was stored in the state from Kudu. And if it manages to enrich it, then it emits it or collects it. But it's also possible that a record comes in from the Kafka side before it has been encountered from in the Kudu table. So in this case, the record is added to a buffer. And when a record comes in from the other side, so the enrichment data from Kudu, then it is stored in this value state, and if there is anything in the buffer, it's cleared out and collected. So once this joining logic is performed and we take care of timestamps and watermarks, we can convert the data stream back to a table. And afterwards, we can perform the same kind of aggregation and alerting logic as we have in the other pipeline.
So let's take a look at some of the key takeaways from this talk. So we've seen that the Kudu and Schema Registry catalogs and integration makes life pretty easy when it comes from data exploration and accessing data from these sources. We have to execute less, create table statements, at least initially. And we get to do more data exploration and prototyping for almost free. We saw that these seemingly simple enrichment joins can still be quite difficult with Flink SQL, as it doesn't properly match the SQL semantics. But we can call temporal joins or some custom solutions to the rescue, and we can definitely make this work and build a pipeline that performs well and does these use cases exactly the way we want it. Thank you very much.
Thank you for listening to our presentation.